We are live now.
Cool, we're live now. Hello, everyone. This is Xibei from DoraHacks. Thank you all for joining us today for the workshop series of DoraHacks Starship Use Cases Hackathon. Today, we have a special guest with us, Keval Dattani, the CEO and founder of Space Power, will be sharing his insights with us on laser power, the next frontier in space. And I'm very excited to be able to hear his insights on this fascinating topic. And I'm pretty sure everyone who's joining today will have some great takeaways. Before we kickstart the session, let me give you a quick introduction about who we are and just an overview of our Starship Use Cases Hackathon. So for those of you who don't know DoraHacks quite well enough yet, we are a leading global hackathon organizer and one of the most active developer incentive platforms. We love to support innovation in blockchain, quantum computing, space tech, and more. And we provide a wide range of toolkits to help developers around the world team up and fund their ideas and projects via our hackathons, grants, bounties, etc. And as we are very much committed to supporting innovators within the space sector, apart from our ongoing long-term space resources and exploration grant program, last month, we launched another bigger initiative to foster space tech innovation, which is our Starship Use Cases Hackathon, with $100,000 in prizes, capitalizing on the potential offered by Starship. We have developed 18 use cases and 2 open challenges for hackers. Our use cases include orbital hotel, space-based farming, routers for global Internet of Things, metals from the moon, etc. 2 open challenges are novel satellite constellations and recreation facilities for space hotel. So through this hackathon, we like to motivate all space enthusiasts out there with engineering skills to build their solutions for space. Feel free to check out the link below in the description. There you will find more details about the hackathon, including background and task description for each use case, hacker resources that our team has curated for you to enhance your solution design, and also the updates about our upcoming workshops. The submission portal is already open now, so you can join the hackathon anytime, and we can't wait to review all your submissions. Lastly, for the audience during the workshop, please feel free to share any questions or thoughts you have in the YouTube chat room. I'll make sure to share your ideas and thoughts with Keval and ask your questions during the session and at the end of our session in the Q&A. Now, without further ado, I'm excited to let Keval have the stage. Welcome, Keval. Thanks so much for joining us today. Why don't you briefly introduce yourself before jumping into the workshop content?
No, fantastic. Thank you, Xibei. Yeah, my name's Keval Dattani, founder, CEO of Space Power. My background was in nuclear engineering until I started to think about power uses in space. And really the big kind of change was we don't need megawatts today. But the question is why can't we put things like Ryzen 9s or, top GPUs in satellites and utilize those in space? And then that kind of really started to drive me towards thinking about alternative power supplies and auxiliary services, and came out with Space Power. So definitely, if you've got any other questions, feel free to ask them through the presentation, and it should be a bit interactive and a bit of a workshop. So yeah, feel free to just pop up any questions as they come up. So there's slides up.
Yeah, I will keep an eye on the comments in the chat room, and I will definitely let you know, Keval.
Great, thank you. So yeah, Space Power. What we're really trying to look at is laser power in order to help satellites get access to energy and basically allow them to use more energy while still using smaller solar panels. So we see ourselves really useful for low Earth orbit constellations, and I'll go through a few of those use cases and really what do we mean when we talk about low Earth orbit satellites and what are the typical kind of like styles and like why we want to use those. We've got the more traditional geostationary satellites. These are the ones that give you the big communications. But also the really interesting cases and the stuff that I really enjoy is thinking about permanently shadowed regions of the moon where you don't get any sunlight. How does that restrict your missions, and what else could we be doing when we've got extra power? And really what we want to try and do is to get to this LEO power grid constellation where you can just power up your satellite whenever you need some extra energy. You just make your little subscription demand, and then we'll go and beam it over to you for your mission. And really allows you to minimize the size of your satellites and the number of satellites that you need in your constellation. And this is kind of like what we've been seeing for a while. Things like SpaceX have really dropped the launch costs for satellites over the last 5 to 10 years. And as we start to see these kind of drop down, so many more use cases start to come out. So we can see lots of Earth observation, telecommunications, data processing. And I think, as Sibe kind of like mentioned earlier with some of the use cases and some of the businesses that you've been seeing, they're kind of really starting to get into more futuristic kind of applications like space farming and orbital tourism and hotels. And this is where we kind of see ourselves, where it's cool when you have these ideas and the big vision, but then when you start to think about the practicality, how are you going to make it? That's going to be a big theme about this little workshop. And hopefully that should start to bring out some of those ideas of what are the enabling technologies and the extra businesses that we're going to need as an industry in order to kind of grow and give ourselves this super high internet anywhere in the world, and try to really start boosting what we can do from space and how we can help people back on Earth. So one of the big things here is everyone uses the sun. That's your power source. And as good as the sun is, it's been shining for a very long time. It gives us lots and lots of energy as well as the planet. But when you're in the shadows, you start to lose access, and the sun's not getting any more powerful, thankfully. But that does mean that you've got this kind of fundamental restriction on how much power you can get out with a small satellite. And this is where I think the really big changes started to happen, where, okay, we can make do with what we have, which is how we've been starting to get Google Maps and these satellite images and really starting to help us get better informed about climate change. We now want to start pushing into much higher power use cases. And so suddenly you have this problem. Are you going to double the size of your satellite, which then doubles the costs, either makes your launches more expensive and also slightly harder to book? Or are you going to basically restrict yourselves to smaller data rates? And this is one of the big surprises, I think, for me when I started to look at the industry, is typically one of these small satellites, and it's kind of like the size of a shoebox, if you can imagine that. All it can power is about 80 to 100 watts for 2 to maybe 5% of the whole time that it's up there. So you imagine you're spending like $5 to $10 million on this machine that you can only use like 3% of the time. And it's 2 light bulbs. It's not even that really, we're not really pushing those big cases where we can have things like thermal modeling or thermal imaging or radars that really then start to help get more informed about what's out there. And we also start to see that as soon as power is such a critical issue that if you start to lose your power supplies, your whole mission, your satellite is out of control and it starts to become orbital debris. So we're starting to then see waste generation because of power failures. And this is where we want to really start to help alleviate this. And it's a really good idea to kind of think about the two areas and the two types of satellites quite differently. So we can look at LEO satellites. These are the small sats, the size of a shoebox. And what they do is allow for very cheap missions or comparatively cheap missions. But you can gather a lot of data from that bird's eye view and really start to help inform what your business is, and ground stations. How do you react to over mining? How do you react to over agriculture or droughts or forest fires and things like that? So you get quite a lot of detailed information by being so close to the Earth. But because of that small form factor, they are restricted on the power. The geostationary satellites on the other side, they're huge, and typically they work on something like 15 to 20 kilowatts rather than the 80 to 100 watts of a LEOsat, but they're kind of as big as a fridge, and then they've got the solar panels outside. So they start to power themselves. They typically operate over a whole continent, so they'll provide TV for North Africa, for Middle East, for North America, for half of North America. That's the kind of scale. So they kind of live for about 15 to 20 years as opposed to about 3 to 5 years from the LEO side. And so you can see that the amount that you'd have to spend typically also goes up to about $500 million up to $1.2 billion for one of the geostationary satellites. And so you can see that there are two really fundamental different markets and essentially geographies in space. And this is what Starship is really starting to allow, is the low Earth orbit satellites to be used more and bring down those costs. Whilst also, when you think about the further, like the large cargo capabilities, you can then start to launch geo-style satellites much further for lunar colonization and things like this. So this is basically how we fit in, particularly with low Earth orbit satellites. Typically sitting in a cluster where we can start to share power across to the satellite that needs it the most. And one of the key things that we found was no one wants you to touch the satellite. So the original idea really was, I'm going to have like a Christmas tree of batteries that are just charging, and if you need some extra power, we'll go take that battery out, fly it to your satellite, plug it in, and then you get your extra charge, right? There were some big issues. You spend so much time and money getting the satellites up there. You don't want any damage to them because there's nothing you can do if it starts to if you've got any physical damage. So really the wireless kind of like a wireless power had to be the way to go. And then thinking about lasers, really directional, very direct, and they use solar panels as well as the receiver. You don't need to ask anyone to change the design of their satellite fundamentally. And it's a really cool little area. We've been developing quite a lot of new methods of transmitting that power, and really trying to help push up those efficiency levels and enable ourselves to work quite strongly with the satellites that are already up there. So the technology really comes in some six main subsystems, right? You have to collect the energy from somewhere. That's either from your solar panels. This is how we're looking at it. If we look at lunar applications, we could use nuclear reactors. We then store that energy, typically using some batteries, whether they're lithium ion, sodium ion, or any of the newer kind of like energy storage techniques. You can even use Stirling engines to store power and then release it when needed. And then really this is the cool bit, the energy transmission. So this is the lasers and the solar panels. and then you've got your satellite on the other side. So this is kind of like what we look at, and we start to build up quite a lot of different designs. So here we've got some simulations with our thermal models, figure out how we're going to basically make it work. In the form factor, we've got our beaming and our laboratory satellites. And then also, this is my little favorite thing, Teddy, which is my little robot PV terrestrial demonstrator. So essentially, this was like my Christmas present for myself last year. You've got a little remote control car, and it's partnered up with this camera and laser system. And so the camera can automatically recognize the car. You can drive it. The idea is that you can drive it forever without having to recharge your remote control car. And then you also start to get the power feedback back at home to see how much power you're receiving. And basically, it's going to be a test bed for us whilst we play around with different types of lasers and really push the power levels up. And really, the kind of main area that we're looking at is Starship and these massive structures. If you look at some of the big flagship projects that are happening in space now, it's really talking about space-based solar power, these massive structures, mega structures that we're going to have in space, and they're so big. We're thinking about 6 kilometers wide, 10 kilometers tall, in order to create 2 gigawatts per power plant. So these things are huge mega structures. They're going to need, even with Starship, you're probably going to need 5, 10, maybe 20 launches. When these proposals were initially came out back in the 80s and the 90s, the predictions were 200 to 400 launches that you needed for the rockets that we had at the time. So looking at the Saturn V's and some of the bigger fairings that you can put on there. So this is basically one of the big areas that has there's a gap in the industry. How do you put these structures together? By being able to offer methods of assembly which basically allows the designers of these huge structures to use cheaper, more traditional joining techniques and manufacturing methods. You can actually really significantly drop the cost of these massive programs. So the more complicated the actual work is going to have to be for the designer is just going to increase that cost multiplied across the mega structure. So if you think about how many joins or welds and the maintenance, even cleaning the panels or replacing panels whilst they're in use, these satellites should last about 15 to 20 years. All of these side economies and industries are crying and begging for people to kind of come in and provide solutions. And there's some really cool things that I've seen. Imagine like just a floating robot arm with a welder on the end. And you've got this problem, right? How do you create an arm that's small enough to fit into the little areas, the hard to reach kind of places whilst you're creating this? If you think of how you build a skyscraper, but in space, you start to think about the challenges that you'd expect. How do you make sure it's small enough to fit in, but it's also got enough power, and therefore it needs to have quite a lot of solar panel size and a lot of area for power generation. The lighter and the smaller you can make it, the more efficient that whole process is going to be. So these are the kinds of ideas that I think are going to be really crucial in moving the industry forward and making the most of the capabilities that something like Starship basically offers the industry. So that's basically the presentation, and I'm pretty happy to answer any questions that may have come in. Sorry, you're on mute.
Apologies, I was muted earlier. Yeah, I'm just checking the comments from the YouTube chat room. Guys, feel free to ask any questions here. Okay, I think it's a good idea that I ask Keval some questions from our community, since we have you here. So our first question is, at the distances of hundreds of or thousands of kilometers, how would you deal with like laser beaming tech for space? What comes to your mind for this question?
Yeah, that's a great question. Really, so yeah, absolutely. The further the distance is, the more difficult it is to control the laser beam. One of the best things about this is that because we're in a vacuum, we're in the best possible environment to help maximize that beam, at least how it travels through, well, between the two spacecraft. It's it's obviously not traveling through anything, but the quality of the laser is essentially going to be what is going to drive that. So today, as we're kind of like starting, our ranges are in in the range of 5 to 10 kilometers, and that's good enough for starting up. And then as we've got our plans in our R&D to basically start to build up those lasers, much higher quality kind of beams, and that should then allow us to beam much further distances, something like 100 to 500 kilometers. Absolutely.
Awesome. Thanks so much for the detailed explanation. I'll jump to the second one. A network of space-based power distribution satellites could also be used to serve as a system of routers for optical communications. For instance, a spacecraft that wants to send data to the ground, but which finds that there's too much cloud cover, could instead transmit the data to a nearby space power satellite, would then connect it to an optical ground terminal or route it to another space power satellite. So what opportunities are there for a dual use power or a data satellite network? If you could explain a bit. Yeah.
Yeah, so it's quite an interesting concept to be able to use. We're using lasers today for intra-satellite communication, but the quality of your beam has to be quite different. So as you're kind of pushing up higher power levels, really the beam, I mean, it's much easier just to deliver power. It doesn't really matter the order of the photons. That's not going to change the information. There's no information that you're trying to communicate across and to transmit. As you start to add more requirements to that light, you have to be a lot more precise in how you generate it, how you control it, and then how you send it. So either you can do the dual use, but I'd assume you'd be very restricted on the distances that you'd be able to transmit. But for us right now, it's just an easier MVP to concentrate on the power, and then basically look at whether communications can come in afterwards. But really, it's much easier to do power lasers. But then optics as well to send it back down to the ground doesn't really make too much sense. Firstly, you've got issues with planes, right? I could get into trouble now for shining a little pocket laser into the sky, and it's quite, get into quite serious trouble. So when you're starting to think about sending beams of light with power through the atmosphere, there's a lot of regulatory issues that you'd have to think about and overcome. But that's where the microwaves are coming in, and that's really I think that's the strength of the space-based solar power concept, is when you can then change over to something like microwaves, where you don't care about the size of your receiver. It goes straight through cloud. It'll go straight through the atmosphere. It's not going to get disturbed. And I think that's one of the key benefits of using microwaves for earth transfer.
Got it. That totally makes a lot of sense. And thanks so much for elaborating more on that. We'd also like to know what risks are there to satellite operations while receiving power. For instance, could a space power laser beam blind altitude determination sensors, and could it interfere with scientific data collection? What's your opinion on that one?
I think, there are many different types of technologies that you can use for each of these sensors. And if it's a light-based thing, there's always the possibility, like there's always the option of filtering out the specific wavelengths that we use on the lasers. But essentially, as long as we're staying under the power density of the sun, if your sensor is okay in sunlight, you'll be okay with the lasers. So that's not really a problem until, really we start putting nuclear reactors matched up with the lasers. So let's say we're doing lunar power beaming. You would then have some, you then have an environment that you could fully control. So everyone's going to need to have helmets, and on those helmets you'd have filters, and you could filter out specifically the laser light wavelengths in order to keep everything safe. So you've kind of got this natural development cycle that allows you to keep being safe. So it's safe as it is today because we're not really pushing the technology to its max. But as we start to push forward with higher density energy sources, we can then start to control the end-to-end environment and where that laser light goes, or even specifically protect any really sensitive, fragile equipment.
Got it. Thanks for sharing that information. Lastly, from our team, what do you think are the prospects for commercial satellite servicing, which would include space power, but also orbital debris removal and robotic repair?
Yeah, like as I kind of touched on, talking about the Starship uses and where the industry is going. I think this is the massive gap that exists in such a fun ecosystem where you can come up with so many different ideas and start to build this, I think, in orbit community of welding robots, of propellant recharging robots, 3D printing, so you can manufacture spare parts for satellites or for space-based solar power systems whilst you're there. How can you do mining either on the moon or on Mars? How are you going to transfer the material and the utilities that you need? Deep bore. One of the cool ideas that I heard was deep mining on Mars, and this is one of the, I think, the fun ways of trying to explore the problems in such a different environment. You might just think mining on Mars is going to be like mining on Earth, but simple things like diesel engines that you count on to provide you energy at the bottom of the pit isn't feasible, right? There's no atmosphere. How do you send energy down into the deep bores? It's a totally new problem set. We've got some experience already, but I think it's a really fun kind of method of looking at a problem that we've solved on Earth and then trying to then understand why can't we use it in space, and then solving those problems. I think is a fantastic thing, and it's going to be this in-orbit servicing and maintenance, repair, utilities that I think are going to be fundamental to kind of like build the foundation for where the industry needs to go.
Got it. Thank you, Keval. I'm also wondering, since our team came up with so many use cases for our hackathon, like we came up with the use case like climate engineering, the easy way, essentially to build a shield to block the sunlight from our Mother Earth, and also like to build routers of global Internet of Things. Like in general, what are some of the use cases that you personally feel most exciting and you find most promising so far?
I think that, yeah, robots. I think I just like the idea of having of seeing autonomous robots kind of flying around and doing jobs and working in space. You mentioned orbital hotels, or I think that for me that's the exciting stuff. It's what is it that I've seen as a kid on TV, either in Star Trek or Thunderbirds and this kind of stuff, and actually starting to see some of these ideas become businesses and actually starting to see them kind of like become more real. I think that's the really exciting part.
Definitely, yeah. That's the future of space exploration is full of possibilities. So really looking forward to see what new technologies are coming and what we can build using those technologies. And lastly is my personal question for you, Keval. What advice would you offer to aspiring space tech innovators, especially those young students, young engineering students who aim to make an impact in the space industry?
Yeah, I think it's about self-belief, really, but and the paradox that you always get with, you need to take advice from people who will help you on your journey, especially if you're doing this thing to make an impact. You're clearly doing something that no one's been doing before, something that's wildly different, and you're kind of walking your own path and making your own kind of your own project and program. Other people aren't going to understand it as well as you do. You're the only person that's thought about it for so much in so much depth. So you'll always get, it's natural that you'll get skepticism and questions, even from a good place, to just make sure you're not going to do something wrong. But it's having that self-belief, and you test your own idea with yourself. If you don't believe in your idea, no one else is going to believe in it. And so how do I think it's a really interesting process on how you take in advice, test your own kind of like system, test your own belief and your own understanding of your business, and then help that guide the way that you go forward. So not letting it kind of like beat you down and take all of that negativity, too personally, but really kind of like understand how to take it in and use it to the best, to make your business a success, to turn your idea into to give it the best possibility and highest probability of succeeding and making that impact. But self-belief, yeah, for sure.
Got it. Thank you. I totally agree with you in regards to how important to have a strong self-belief to keep that innovative energy. Let me just quickly check if we have some more questions or comments from the live audience. Let me quickly do that. Cool. I think we're coming up closer to time here, and also audience, everyone in the audience, if you guys come up with some more questions, feel free to reach to Keval through LinkedIn. I think LinkedIn is a good way to reach Keval, and also alternatively, feel free to reach to us, DoraHacks team as well. We'll try to answer your question as best as we can. And so once again, thank you so much, Keval, for joining us today and giving this great workshop. It's incredibly insightful and inspiring. So really appreciate it.
No, thank you very much for inviting me, Shibe. Thank you.
Our pleasure. Yeah, so before we wrap up, I want to say once again that our Starship Use Cases Hackathon's submission portal is already open. We have prepared a prize pool of 100,000 US dollars and thoughtfully designed 18 use cases and 2 open challenges for you to tackle. We are very excited to have launched this hackathon, and we can't wait to review all your submissions with innovative solutions for space. We encourage everyone who has a passion for space to join us and shape the future of space exploration. And if you want to learn more about this hackathon program or DoraHacks in general, please feel free to click the link in the description to the hackathon page. And we do have more space-related live sessions in the pipeline for you. So make sure to follow us on YouTube and Twitter at DoraHacks so you won't miss out on any of the upcoming sessions. With that being said, I want to say a huge thank you to Keval once more for being here with us, giving this wonderful workshop, and especially since you're still sick and coughing and like that. So really, really appreciate your time. And I want to say thank you to all the audience for joining us today. We will see you soon. Have a great one.
Thank you. Bye.
Bye.